Namaskar, I am Dr. Lakshman Mathur from BIT Mesra. This webinar introduces learning-driven autonomy in mobility and socio-economic dynamics. The central message is that autonomy should not be blind automation, it should be disciplined decision support under uncertainty. Here in the pipeline, heterogeneous data are converted into a belief state BT. From this belief, the model generates plausible features FTOQ. A risk-aware optimizer selects one safe and robust action and feedback updates the next belief and model. We do not move from one prediction to one action. We move from many plausible features to one robust action. The same loop applies to autonomous mobility resource systems such as irrigation and socio-economic planning. To make this possible, the first requirement is constructing a reliable belief state from heterogeneous and partially observed data. Now, we will discuss about the first task, multisensory perception and belief. This slide explains how partial observation become a decision-ready belief state. Real systems are only partially observed. Sensors may be noisy, some data may be missing, and action execution may differ from the planned command. Therefore, autonomy should not act directly on raw observation. It should construct a belief state PT. The, the state contain a tried up three special kind of perception vector. Context perception include soil, weather, crop, camera, lidar, radar, maps, terrain, and environment state. Control perception compares intended commands with measured actuation and hardware state. Plan perception adds target, safety bands, resource budget, missing priorities, and constant. The tried equation is like that BT is equal to uh, a phi of CT, phi of UT, and phi of PT. CT is the context vector, UT is the control vector, and PT is the plan vector. Each modality is represented through an embedding and fused using reliability weights, mass, or attention. Belief is not just perception, belief is perception plus control, feedback plus goals and constant. Once belief is available, the next question is what feature could happen if a candidate action is attempted. So next, we will discuss about multimodal forecasting. This slide introduces multimodal forecasting using conditional variational autoencoder and optional diffusion refinement. In uncertain environment, one average feature can be unsafe. Another vehicle may stop, turn, accelerate. Soil moisture may evolve differently depending on weather or ET. Traffic demand may rise or fall. Therefore, the model should generate multiple plausible features. An input includes sensor stream, logs, maps, infrastructure data, weather, demand, signals, actuator, feedback, and plant constant. Forecasting model are here like this. It, it, it is a conditional variational autoencoder samples a latent variable Z to capture hidden feature modes. Different Z values generate different possible trajectories or system evolution. Diffusion can refine preliminary forecast into a smoother and more realistic scenario. Here, FTOPU is the set of K feature produced for belief vector BT and candidate action U. Forecasting should answer what plausible features could happen if this action is attempted. After generating possible features, the system must choose the action that is safest, most robust across those features. Next, we are going to discuss multimodal control and actuation. This slide converts forecast scenario into real-world actions. The controller evaluates candidate actions across the scenario set. The objective is not only to minimize average cost, the controller must also penalize tail risk, avoid violations, respect hard constraints, and execute only feasible actions. Scenario set to candidate actions, risk, and constraint scoring. Plant command UT star optimal control. Execution, actual execution AT observation and update. The real world may not execute exactly what the controller planned. Hardware delay, saturation, faults, pressure limit, or compliance gap. This can cause AT to differ from optimal UT star. The residual, uh, the difference between AT and UT star update the next blip and can tighten uncertainty margin. Human-centered check we have to perform so that uncertainty should be displayed, intervention rationale should be logged, approval should be required where necessary, and outcome must be monitored. This control logic is general, but the action and constraint differ by domain. So here I will talk about domain-specific control and actuation. This slide saw that one optimization logic can support several domains, while each domain has its own action space and constraint. The optimizer is shared, but the actuation channels are domain specific. In mobility, actions are steering, braking, throttle, and route choice. Constraints include collision avoidance, road geometry, speed, acceleration, and comfort. For irrigation, action includes pump on or off or speed, a valve, schedule, flow rate, and duration. Constraints include moisture bands, pump pressure, energy cost, and valve switch limits. For socio-economic support, action include signal timing, transit display, transit dispatch, messaging, and resource allocation. And constraints include a budget, capacity, fairness, rules, and emergency priority. So objective is like here, the action UT star minimizes scenario cost, risk penalty, and actual mismatch, subject to feasibility constraint. The same mathematical control structure produces different decisions because of the action channels and constraint change. Now we apply this framework first to autonomous mobility. The first application is about autonomous mobility. This slide introduces autonomous mobility as the first application. Autonomous mobility is not deterministic lane following. It is interaction forecasting under uncertainty. The vehicle must reason about road geometry, other agents, traffic light context, and occlusions. Bird eye view first. We will talk about bird eye view semantic maps that provides a structured representation of roads, land graphs, agent boxes, predicted paths. Conditional variational autoencoder generates many possible future trajectories. Nearby agent may go straight, slow, or down, turn, merge, stop, or interact. A risk-aware model predictive control filters unsafe or infeasible features and choose a robust steering, braking, or throttle command. Conditioning on agent history and bird eye view latent context improve multimodal prediction performance with a residual baseline. Safer mobility comes from predicting a distribution of interaction features, not only the most likely path. The next slide gives a dataset grounded view of this mobility pipeline. This slide explains the dataset grounded conditional variable autoencoder pipeline for mobility. The model uses 10 frames of agent history and a bird eye view tensor of size 224 by 224 by 25. The bird eye view tensor captures traffic scene context such as road geometry, lane structure, and semantic layout. Variational autoencoder scene latent captures scene information that is compressed into a latent representation so the model can use context efficiently. The second model of variational autoencoder combines agent history and scene latent information to generate three or more probable future trajectory with probability or mode score over a 50 frame horizon. Agent motion alone can be ambiguous. The same short history may lead to different features depending on lane geometry, traffic lights, or neighboring vehicle. So this feature helps score candidate maneuver, avoid collision features, respect vehicle limits, and replan with feedback. The AV regions over many possible agent features before selecting a maneuver. The same closed-loop logic also supports resource systems such as smart irrigation. The second application is smart irrigation. This slide introduces smart irrigation as the second application. Smart irrigation is a natural example of learning-driven autonomy because of the system must decide when, where, and how much water to apply under uncertainty. Soil moisture indicates current and future water availability in the root zone. ET indicates crop water demand. If the system only uses a soil moisture threshold, it may react too late. If the system also forecasts ET, it can act before a stress occurs. The 90% prediction interval shows when the forecast is uncertain. Wider interval suggests the controller should be more cautious. The model pretty control chooses valve or flow commands while respecting moisture band, pump pressure, energy cost, and valve switching constraint. A smart irrigation becomes autonomous only when forecasts are connected to safe, efficient, feedback-corrected actuation. The next slide explains how learned irrigation context becomes part of the belief state. This slide explains how learned irrigation context can be interpreted, interpreted and used for adaptive control. Each point in the PCA plot represents a 64-dimension context vector compressed to two principal components PC1 and PC2. The color indicates time, so the plot shows how irrigation context evolved during the runtime or season. If early time and later time points occupy different regions, this indicates changing regimes. These regimes may reflect crop growth, soil condition, changing weather, or water demand. These context vectors are fused with actuator results, residuals, and plan constants to form the belief state BT. When the system detects a different regime, the model can adjust latent anchors, uncertainty as spread, risk margin, or scenario count. So PCA is not only a visualization, it helps how learned context becomes interpretable and decision ready. The next slide shows how these forecasts are converted into irrigation action. This slide closes the irrigation loop from conditional variation autoencoder forecast to safe actuation. The goal is not merely to forecast soil moisture or humidity. The goal is to use forecast to decide irrigation actions. True and predicted soil moisture may diverge at some horizon. Uncertainty-aware control prevents overreaction to a single predicted value. Predictability captures crop water demand. If highest it is expected, the controller can water anticipatedly before moisture falls below a stress level or threshold. The model predictive control evaluates candidate valve and flow commands over multiple moisture and AT scenarios. It balances crop stress, water use, energy cost, pressure safety, and valve switching. Each scenario contains possible soil moisture, theta, and ET features. The controller selects the action that perform well across those features. Forecasting is useful only when it closes the loop. Predict, optimize, actuate, observe, update, believe, and transition as today I had seen. This third assumption moves from physical actuation to socio-economic planning support. This slide introduces socio-economic decision support under traffic flow signals. Socio-economic supports become concrete when planning decisions are connected with observable reality signals. Here, daily traffic burden and mobility stress are used as measurable signals. The profile saw peak volume of 3,545 pc at 8, lowest velocity of 2.5 at 18, and peak B/C ratio of 0.249. These quantities help describe when and where mobility stress appears. The planner's blip may include volume, velocity, V/C ratio, infrastructure load, public transition ability, roadside activity, and policy response history. The system can produce low, medium, and high stress features for congestion, service delay, source demand, and policy impact. Intervention may include signal timing, ramp metering, transit dispatch, variable messaging, and hotspot management. The model ranks options and display uncertainty. Human planners approve and monitor actions. The next slide converts traffic profile into a stress scenario. This slide explains a stress scenario construction for traffic flow decision support. Abstract socio-economic stress can be operationalized through low, medium, and high stress traffic scenarios. This makes planning more proportional and accountable. During free flow period, the system should mostly monitor conditions and avoid unnecessary intervention that we term as low stress. In high stress, during pre-peak or corridor loading, planners may adjust signals, inform drivers, and uh, prepare transit support. In the high stress during peak burden, a stronger intervention may be considered, such as green wave coordination, hotspot management, and public transit reinforcement. The blip state combines vehicle data, infrastructure, modality, situational contact, and socioeconomic information. This slide presents the complete closed-loop architecture for socio-economic planning. Data stream first pass through quality check, then they perform a belief state. A scenario generator produces a possible stress feature. A risk and filter module evaluate policy options. Finally, planner approve actions and observe outcome update the next flip. Belief state includes state variables, uncertainty, missing data, mask, source, reliability, weight, policy, response history, and operational constraint. It considers low, medium, high stress features are rare but costly events, demands, and capacity trajectory, spatial spillover, and scenario probabilities. Risk-aware planning. The model minimizes expected loss, analyzes tail risk, respects budget and capacity, compares interventions, and documents trade-off. Human approval is required, audit trails are stored, fairness checks are visible, impact is monitored, and feedback corrects future planning. This is not autonomous enforcement, it is planning evidence for accountable human choice. The final slide summarizes the overall values of the framework. To conclude, learning-driven autonomy is not only about automation, it is discipline, decision support under uncertainty. The webinar connected perception, belief construction, multimodal forecasting, risk-aware optimization, safe actuation, and feedback. Action must respect constant and avoid unsafe feature. The system should learn from observed outcomes and actuator feedback. Uncertainty assumptions and intervention rationale should be transparent. Final accountability should remain with people, especially in public domain system. Public autonomy should make better action possible, safer, greener, more resilient, and accountable. Thank you. I welcome questions, discussions, and collaborations.